Okay, so let's get started. So my name is Jun, and this is my colleague, Viswa.
Hi, guys.
And we're both from eBay, the platform and data infrastructure team. And today I'd like to present to you the Sharded and Federated Prometheus cluster to debug this and monitor the database. So over the last 3 years, we have developed a geo-distributed database in eBay called NuData. And today we have deployed the NuData in eBay, the internal data centers with thousands of ports and over the Kubernetes infrastructure. So we use a Prometheus 2.3 for metric monitoring. And we use this metric monitoring system to help us for the system operation and continue the system development. So just to give you a brief overview of this system at the high level, so we had this client library that is attached to the database application. Then we route the request to the service tier. The service tier then end up into the backend database. In the backend database, we had the proxy to process the query request, and then the request persists, and then the results persist to the backend storage engine. And it also can create the indexes when necessary and push the index to the global secondary index store. So just to give you a little bit detail about this database framework in order to set the context for the rest of presentation. So the customer can create the multiple key spaces, and each key space is considered multiple shard, and each shard consists of multiple replicas. The replica can be the master, can be the secondary, and can be the called hidden. And hidden is actually for the purpose of backup and recovery. And so all the replicas within a single shard is actually scattered across multiple data centers. So in this database framework, we have this hierarchy of replica, shard, and key space. So for the rest of the presentation, we're going to cover how we're going to capture the metrics and aggregate the metrics. And then we're going to describe to you the sharded and federated cluster that we have developed to handle the metrics scraping and then metrics aggregation. Then we're going to describe you the solution that we have to route the time series requests among these time series database cluster and then get the result and then present the result in the visualization environment. And then we're going to share with you some monitoring experience that we have for system operation and the system development, and finally the conclusion. So in this database framework, we capture throughput, latency, error, the queuing, the saturation, and then the states. The state can be like master, replica, and master and secondary, or can be the Prometheus up and down. And we rely on the Kubernetes to expose these OS metrics, and that Kubernetes is hosted in each of the host machine. Also, we develop and install the custom metric exporter to capture for example, the I/O disk metrics. That is a much richer compared to the default Kubernetes OS metrics with respect to the disk operation. And so overall, we capture about 20 million metrics instances per scrap interval. And the scrap interval today we define it as 1 minute. So each day in each data center, we capture about 195 gigabytes of the time series data. And we had the 2 data centers to host this Prometheus cluster. And we had the retention time is set at 7 days today. So the integration of the Prometheus with the Kubernetes actually brings a lot of nice features. For example, it can automatically scrape the target in our cluster. So whenever you have the server bring it up, then it automatically gets scraped. And then we also can filter the server, the target based on the auto-discover the labels. Then also we can have inject automatically the metrics labels into the metrics based on the label that's specified in the port spec. So now with the label, one of the things that we can describe is a hierarchy. So there's 2 kinds of hierarchy that we describe. One is the physical hierarchy, so you can describe the port, the host, the rack, the data center, and then the logical hierarchy is the one that I described to you, that you can have a replica, you can have a shard, and have a key space. So all these labels actually automatically injected into the matrix based on the port spec. So we don't need to write the code to manually inject these labels. So with the labels to describe the hierarchy, then now we can aggregate the metrics across the hierarchy. So this is just give you an example on the DB process total, which is a counter, and with this counter, then we can compute the transaction rate at the replica level. Then we can sum the transaction rate at the shard level, and then at the key space level, and finally at the namespace level. So on the right-hand side, what you can see is actually you can aggregate the metrics along the physical hierarchy, namely that you can get the host level metrics, you can have the host level transaction, the rack level transaction, and then the zone level transaction, and then finally reach the same namespace level transaction total aggregation. And we also see that we can find out that actually the key space is a constraint at the right-hand side, so that all the host level rack and zone aggregation is actually constrained by the specified key space. So I just mentioned earlier that we had 20 million metrics that we need to scrape for each instance for 1 minute. So this is difficult for us to have one single Prometheus instance to scrape all of the metrics. And in addition, there's another difficulty is that we have over 1,200 recording rules to handle the real-time alerting and real-time dashboard. So the reason why we have so many of these recording rules is because that each metric tied to many dashboard. And each dashboard is tied to aggregation hierarchy that I described to you earlier in the previous slide. And also I'd like to point it out that in our Prometheus instances, the CPU consumption that devoted for this metric aggregation or recording rule evaluation is much more significant compared to the amount of the CPU that you spend on the metric scraping. So just you cannot just, okay, I have a scraping and done. No, actually most of the time is spent, most of the CPU is devoted for the metric aggregation. So that brings to the next topic that I hand it over to Viswa to cover this Sharded and Prometheus cluster design.
Hi all, my name is Viswa Vutharkar. I work on metrics monitoring and alerting in the data infrastructure team at eBay. So I'm going to spend the next few minutes talking about how we set up a sharded federated Prometheus cluster and deployed it to production at eBay to monitor the geo-distributed database that Jun talked about. So I'm showing here a simplified example where the target space, the thousands of pods across hundreds of shards that we have, you cannot monitor with a single Prometheus because of the amount of metrics that we collect and the rules and all of that Jun mentioned. So the logical thing is to try to add more Prometheus servers, but in such a way that we can scale the Prometheus setup proportionate to how the geo-distributed database is also going to scale. So in this simple example, if you add one more Prometheus and take half of the pods, for example, the pods which have even numbered shard IDs and the pods which have the odd numbered shard IDs, and get them scraped by 2 different Prometheus servers, you already kind of reduce the load by 50%. So we take this concept, generalized it. Prometheus has this nice Hashmod function, and you can apply it strategically to certain set of labels, and then achieve your targets can be grouped into more than 2 groups, n number of groups, however you want it, like you can cut and slice them, right? So let's look at how it looks like. So at the top, you see the gray box, which is our Prometheus YAML template. So we have templates for the Prometheus job, for recording rules, for alerting rules, for our secrets, config maps, all of the Kubernetes artifacts. So they go into our automated script setup, and we churn out the actual deployment artifacts and secrets and so on. So here, if we take the example of we want to split the target space into 2 groups, the automated scripts substitute the templated variables, and you can see in this example the modulus remains 2, but the regular expression 0, 1, 2, 3, 4, 5, based on how many you want, right? So by using the key space and the shard ID of the target pod as the input to the Hashmod function, we also have this nice side effect that all the pods belonging to a particular shard of a particular key space, they get scraped by the same Prometheus. And it's a little bit key, as you will see later, it helps us in writing aggregation rules in a much easier way. So we talked about the scaling of the Prometheus in proportionate to the growth of the data store. The next challenge to tackle is the high availability, and that's pretty straightforward. Taking the same example, Prometheus 1 and Prometheus 2, we replicate that exact setup in a remote Kubernetes cluster in a remote DC, and you get a pair, Prometheus DB1, Prometheus DB1 standby, and DB2, DB2 standby. Each forms a HA pair, and they are scraping the subset of targets that complete the whole set of target space. So the next way to scale within a target space, so we said we'll scale along the shard boundaries. So using shard as the dimension, you get a number of Prometheus clusters. So we expanded that concept, and gave ourselves another way to scale and also isolate. So we have several categories of pods, if you will. We have the database pods, we have indexing pods, we have service pods, we have kubelets which expose the operating system metrics, and they get scraped by independent Prometheus clusters. So we mapped these categories to Prometheus clusters, so that gives us another way to scale the Prometheus independently. If the OS metrics are getting huge, then we just have to scale the Prometheus cluster corresponding to the OS category, and so on. And all of these Prometheus clusters are again mirrored in the remote DC. And you can see here we also have all these Prometheus endpoints defined as data sources in Grafana. And when I get to the Grafana slides, that I'll describe how the querying happens and how we have made it convenient to the end user as well. So the next challenge after scaling and high availability, obviously, is how do we federate now? Now that we split our metrics across several different Prometheus clusters and Prometheus shards, if you take an example, you want to know total inserted document count. So now your data is split across 2 Prometheus. So what we do is we define, using recording rules, aggregated metrics at the Prometheus shard level. So in the example that I gave, if you aggregate in Prometheus DB1, you get the count for the total inserted documents in your odd numbered pods, and then on the other side you get the total count up to even numbered pods, and then you aggregate it up and at the federation level, and you get the total count across the entire key space. Now we use deliberately a prefix level 0 for all these aggregated metrics that occur on the Prometheus shard level, and that makes us easy to define the federation job. You don't have to worry about how many are defined as long as you follow the naming convention. It's a single Prometheus federation job description that pulls all the level 0 aggregated metrics. Again, the federated setup itself is highly available. We have a mirrored setup in a remote data center which scrapes the same set of all the Prometheus instances. Now, one thing I did not talk about, the Prometheus instance and its mirrored instance, we don't directly go scrape them either from Grafana or from the federation. They are fronted by a load balancer whip, and the federation talks to the load balancer whip. So if the primary is down, the mirror can provide the data. There are several ways the load balancer whip can be implemented: ingress, federated ingress, Envoy, HA proxy. We don't have time to go into the detail, but there's different ways you can implement that. So this is what the completed picture looks like. So we have several categories of Prometheus clusters, and each category can have n number of shards, and each shard is nothing but an HA pair with an active in one data center and the standby in another data center. And all the traffic is pulled through the load balancer, the query traffic, and the federation traffic. This entire setup is deployable within a couple of seconds through our automation scripts. And it's fully deployed out, including the rules and recording rules and secrets and any other things that are needed for the setup to work. So from the Prometheus side, if we go on to the query side, the Grafana side, so I mentioned we use the Hashmod function strategically on a certain set of labels. So now your data is distributed, and the user wants to query not the federated rolled up metric, but say the document count at a shard level. So now does the user have to know about which Prometheus scraped your data shard? So that's the challenge, and we tried to solve it with a couple of techniques. One technique, we are calling it the federated lookup and routing table on the Prometheus side, and then on Grafana, we make use of the Grafana template variables and templated data sources, and I'll go into details. So before that, how it's going to look like for an end user on the Grafana dashboard. So they'll come to this dashboard, and they'll see the key space field and a nice drop-down list of key spaces that they can select from. They don't have to type, they don't have to remember anything. Once the key space is selected, they then select the shard ID that they're interested in, and the data source field is automatically populated. And all the graphs are nicely refreshed for the context that they are interested in. Now, as I mentioned, that is possible by some of these techniques. So the technique on the Prometheus side, we built this special metric that we are calling the routing map. It's built on the up metric, which is generated by default on Prometheus. for every target that is scraped. So if you look at the recording rule in the gray box there, you will see that it's nothing but count of up and aggregated by some strategic labels like key space, shard, and zone. So the instant time series vector examples for corresponding to that metric, you can see the two blue boxes for Prometheus DB1 and DB2. You will see key space 1 and the odd numbered shards, and key space 1 and 2 on the right side with the even numbered shards, right? So this is kind of looking like already a partial lookup table. And then when you federate this and you pull these into your federation server, you can inject other external labels like data source name. So on every one of our Prometheus instances, we added data source name, which corresponds to the name that we give to that endpoint in Grafana when we define the data sources in Grafana. So when that gets injected and you look at the bottom yellow time series list of values, now if you have a key space name and a shard ID, you can find out by a query what the data source name is. And given the data source name, Grafana can go pull the metrics from there. So with that routing map time series in place, now key space is nothing but a label values function applied on that metric, and you retrieve the label values for the key space dimension. And similarly for shard ID, you retrieve the shard ID dimension values for a given selected key space. And the third critical one, once you know the key space and the shard ID, you again apply the label values function, and you retrieve the data source name. So that's how in the dashboard, the data source gets populated. There's a little trick here. In Grafana, the templated data sources cannot be of type query type, so you cannot assign a label values function to it. So we had to create an intermediate hidden variable that has that value, and then the data source templated variable just points to that. So that's all I had to share. I'll give it back to Jun to talk about our production monitoring experiences.
Okay, so the first one I'd like to share with you is monitoring of the monitoring. So basically, once you build this big cluster, so you need to monitor itself. So we come up with a dedicated Prometheus instance called self-mount, and this self-mount is actually scrape all the metrics that expose from the Prometheus instances. So by having all the instances related metrics to be into a single time series database, then we can, so for example, to compare the performance, the behavior that manifested by all of the Prometheus instances. For example, we can see that whether the load that manifested by all the Prometheus shards for the purpose of scraping the OS metric, whether they have the even load or not. Right? So this, and the HA, it's actually applied to these self-bound monitoring instances. So just give you the dashboard that we have. So the first one actually showed that, well, how many time series instances that we capture for each individual instances at this time. So that's the first dashboard. The second one is, well, how many instances of Prometheus in this entire cluster has been down, or currently down. Right, the third one is a little bit more involved, which is just trying to show you that, well, whether there's some kind of deviation of the scraping rate for each instances. Right, so what is the scraping rate instances defined? So here is defined that the rate of there's a particular matrix that exposed by Prometheus instances. It's about the appending to the time series database, and we compute the rate, and we over the ratio, the rate that is applied to the same matrix that computed for the last 30 minutes ago. And so that will give you the deviation. And if you see the deviations get dropped, then know that there's something wrong about this scraping performance. Then so we can attach the alert loop to this self-monitoring. So for example, we can have a threshold to capture how many Prometheus instances are down at this time, and then whether the scrap instances for each Prometheus actually suddenly get dropped. And also we can monitor the reachability from the federation server perspective. And so this is actually the very useful that I'd like to share with you, is actually how we do the troubleshooting, use the metrics-based monitoring system, right? So we aggregated at one of the dashboards to show you the total service error rate across the entire service cluster with hundreds of the service ports. So now it's well, if you see the service rate bump, well, how do you find out that what is exactly the port that you wanted to go inside to inspect? For example, using the local log and then for the troubleshooting. So that's one of the query that we use. Basically, it's actually trying to compute the accumulated error for each service port, and we compute the top 5 of that. And then because this query is actually only invoked to each sharded Prometheus server that scraped this particular service metric. So we had to apply another top 5 aggregation across these sharded Prometheus shard in order to get the global top 5 worst performance. And after that, you can get into the pod and then inspect the local log for the troubleshooting. So this is one example using the top K. Another one is actually we can use we can compute the error rate. And that actually we rely on this Prometheus console. So we saw all of the pod, the service pod, the transient. And we found out that actually Prometheus, one single web console actually can plot hundreds of these transients, and operator or developer can visually identify that what are the worst performance of this that produce the highest service error rate. And we had to do it for all these sharded server. Another one is actually about the aggregation of the database metrics. Right? When you do the aggregation, we need this replica, shard, and then the key space. However, we found that actually it's not possible to aggregate the Kubernetes exposed OS metrics. The reason why is because the port name, it exposed only the port name, and then all these user-defined or these the database associated key space, hierarchy, key space, shard, and replica actually is not captured. So fortunately, we have to expose our internal information, which is that the port name is actually based on the concatenation of the key space, shard ID, and replica ID. So we use the Prometheus config spec and then have the regular expression to attach this OS metric, and then we use a regular expression to extract out the key space ID, shard ID, and replica ID, and then inject it into the Prometheus metric as the additional label. Once we have this label hierarchy, then actually we can sum over the container in OS metrics. So for example, this residential memory, and then we sum over the container, we get the replica level metrics, and from the replica, we get the shard, from the shard, we get the key space, and also we can get the entire namespace if necessary. So that this kind of OS aggregation, it just turned out to be very useful for us to do for us to do this called resiliency testing, or also endurance testing, that we test the system for over the 1 week, 2 weeks, 3 weeks, because when you see whether memory leak has happened, whether the CPU consumption has suddenly changed or not. So this turns out to be very useful. The last one actually I want to show it to you is about alert summarization. So Prometheus comes with the alert manager, but that alert manager mostly is just communicate to you whether the alert has happened or not. So there's not much summarization capability built in. So what we have is that, we will explore this, the knowledge of the Prometheus alert, which comes with the lot of label. The labels come from the recording rule that we evaluate this alert. Right? That comes with the recording rules label. So now we can summarize all this alert with this label. So in particular, we can have a severity. So we can see it summarized over the critical or high or warning. That's a 3-level severity that we define in our system. And we can aggregate it also over the logical hierarchy to see that, if within this data center, how many alerts happen. Right? All the logical hierarchy, for example, you can see how many alert has happened within this key space for the last 3 hours. Right? So, and then we also have the status, which is that the alert whether it's active or actually has been resolved. So this is another label that we can attach to. Well, so Transient database will not be able to solve this problem, so we actually rely on the Elasticsearch that we persist this Prometheus alert into this Elasticsearch and rely on the Elasticsearch to index this alert with the label that we specify. So that's the outcome of the Kibana dashboard. So I mean, not easy to see from the audience if it's too far away. But then we can see that you can have a logical hierarchy, physical hierarchy, that you can do the filtering and aggregation. You can alert severity, and then you can have filing, active filing, or resolve or not. So there's one point is one thing that I want to point it out is actually there's a time window, right? If you can specify the time window in the last 1 minute, 2 minutes, then that you can get the real-time dashboard. If you set it like 1 hour, 2 hours, 3 hours, or 1 day, then that will give you the historical alert summarization. So that turned out to be a very nice tool for the on-call person. So with that, I'd like to conclude our presentation. Prometheus, if you download from the internet, it's actually the standalone single process instance. But in this presentation, we'll show it to you that we can create a horizontally scalable and sharded federated server cluster without modifying the Prometheus source code. And that with this scalable cluster, we use it to handle the real-time alerting and real-time dashboard with this hierarchically aggregated metrics. So with that, we'd like to conclude our presentation. Thank you for your attention, and we can have some Q&A.
Any questions? Yes, please. So we have a webhook alert manager. You can write custom webhooks. So we have a webhook that intercepts the alerts, and then we send it to our internal long-term retention store as well as to Elasticsearch. And in future, we have plans to send it to Thanos and have global query as well as long-term retention through Thanos. Yeah. Yes.
So how does that work? Excellent question. Okay. So we're going to go to this routing table. So I think they emphasized that routing table is a ton-based global local table. So I say ton-based. What does it mean? So this routing information, when you have 2 shards, that routing table information we call it a ton. And then if you know the switching time, so then you know that before that point you have 2 servers. For after that you have 3 servers. Then actually with that you can have a clear boundary, and then you can do that. So we call it continuous sharding. So with this mechanism, well, we just didn't have time to put it there, but great that you raised this question. Say we can actually perform the called continuous sharding in this sharding setup. Yes.
Yes, yeah. So because it's a drop-down list, when the user selects a key space and a shard, obviously, as I mentioned earlier, because of the way we picked the Hashmod function, the shards data is in a single Prometheus. So one Prometheus data source is all we need to display all the shard level data. Yes. So that's where the global query part comes in. So when we started this out, we were actually keeping an eye on Thanos and Cortex and all these other products. So that's where the global query part comes in. If you want something in between fully federated, aggregated versus single shard level, and you want something in between, obviously you need global query there.
Okay, so when you aggregate 2 shards, you had some purpose in your mind, right? So maybe you're going to aggregate it based on some label. Okay, so maybe based on I want to aggregate the 2 shards that it's has manifested a server error rate with ton up or something. So you can constrain with the label, additional label, right? Because you have something in your mind because of when you summarize. Not just only arbitrarily say, okay, I want 2 shards. How do you specify that? Right? There's need to be a systematic mechanism for you to constrain the query.
How are you currently managing your configurations? It sounds like you've got lots of things that would be very small.
Yes. Yeah, so right now, like I said, we have templates for recording rules and the Prometheus jobs and so on, and our automation scripts just take the templates and then based on the input, they generate it for n number of Prometheus instances. It's sufficient for our purposes right now. It's not very complicated. Just with a couple of scripts, we're able to achieve this. But coming to this session here, we came across a lot of other tools that we could potentially use to achieve this deployment automation, and we are going to look at some of those.
It just emphasized, with the same script, we can deploy all these cluster to staging, pre-prod, and then production.
Yeah.
And also there's some kind of security domain, some security compliance, something the special domain we can do it as
PCI
well.
compliant zone. Yeah. Yes, please.
For the metrics that a parent is scraped from children.
Yes, so we have deliberately limited it to only, the federation server only scrapes the already aggregated metrics from the children Prometheus. And that's why our recording rules, we have hundreds of recording rules for aggregating it on several different ways, on several different combination of labels that we are interested in.
Given that, how would you characterize the kind of memory load
Oh, definitely, definitely, yeah. We actually have only one single federation so far. We didn't find a need to have more than one federation because all the load, like Jun mentioned earlier, goes down to the recording rules, and we have so many recording rules. We have all possible kind of aggregations that we need. The federation is just pulling them and aggregating some of them to a level 1 where needed, but in most cases, it's just aggregating them. Yeah. Yes, please. Oh, so
Okay.
you want to go ahead?
So the real-time already come from the Prometheus, and the Prometheus, and then go to alert manager go to the webhook, and then we had a webhook to go to Slack. So that's a real-time alerting is go through this Prometheus cluster, and what we have is that this I use the called alert summarization. This is how the on-call people to digest how the continuous alert stream comes for the last 1 hour, 2 hour, 1 day. I mean that's a categorization or summarization. It's sort of like analytics. It's not the real-time.
Yeah, and also there's one more use case. Whenever we have any production incident, when we want to do root cause analysis, people want to go back and look at what else happened at that time. How did we miss it? How did the on-call miss it, and so on. And the Elasticsearch helps us to look at the history and try to roll it up in several different ways. Yeah. Uh-huh. Oh, so in this case, the active and the standby both send alerts, and we actually have not one but 2 alert managers in 2 different data centers, right? So they both are sending to both alert managers, and we have some logic within the webhook that does the dedupe based on alert signature. So if you look at alert coming from 2 different Prometheuses, almost all the information would be similar, except the start time might be slightly different because they might be scraping at slightly skewed times. And of course, the external label, this is Prometheus DB1, or this is another Prometheus, right, in a remote DC. So we take care of that when constructing the alert signature, and we put it in a temporary cache, expirable cache, and based on that, we just do a dedupe. And for the further downstream, only one single alert goes out. All right. Thank you very much.
Thank you much.